Welcome again, everyone. This is Randy Sandone. I'm the Executive Director of the Critical Infrastructure Resilience Institute here at the University of Illinois. It's my delight to introduce our webinar series for today. It's, as you see in the title, Introducing PRISM, which is the Probabilistic Resilient Interdependent Infrastructure System Modeling. Our presenter today will be Dr. Iris Tien. As infrastructure systems are becoming increasingly connected and interconnected, it's important for us to better and more accurately assess the risk that is posed by this interconnection. And these interconnections and interdependencies are both operational as well as cyber in these days. And so in order to more accurately assess the risk, it's critical to be able to capture the varying dependencies and interdependencies that exist across these networks. So vulnerabilities in infrastructure systems can stem from components in the network itself, where elements of the system are located, and from components in totally other networks upon which they depend. This is particularly acute when you're crossing borders, which could be jurisdictional and could be operational, as in the case of the interdependencies, for instance, between a water filtration system and the electric power grid. In today's seminar, Dr. Tien will discuss research work that she's conducted here at CIRI regarding interdependent infrastructure systems. She'll provide a definition of infrastructure interdependency types and discuss the creation of an approach to probabilistically assess infrastructure systems that is informed by a clearer understanding of these interdependencies. She will introduce the product that I identified, PRISM, which is a new tool that Dr. Tien has developed here at CIRI to perform analysis of interdependent infrastructure systems. PRISM enables varying infrastructure interdependencies to be captured and a probabilistic analyses of system performance to be run to assess infrastructure performance under varying threat, hazard, and retrofit scenarios. And she'll describe the capabilities of the tool and provide examples of inputs and outputs for the use of the tool. Let me tell you a word or two about Dr. Tien. Dr. Iris Tien is the Williams Family Associate Professor in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. She joined the faculty in 2014 after receiving her PhD in Civil Systems Engineering from the University of California, Berkeley. Dr. Tien's research interests are in probabilistic methods for modeling and reliability assessment of civil infrastructure systems. She has a unique interdisciplinary background that encompasses traditional topics of civil engineering, sensing and data analytics, stochastic processes, probabilistic risk assessment, and decision-making under uncertainty. And her work on interdependent infrastructure systems modeling and analysis has twice won first-place paper awards in resilient critical infrastructure. Dr. Tien's research has been funded by the National Science Foundation, Department of Homeland Security, U.S. Department of Transportation, and the National Institute.
Okay, never mind. I'll just leave because I cannot speak.
You can't speak. You are speaking. You're telling me to put my phone away while I'm driving. I've already.
Can we mute all phones? Okay. Sorry about that, ladies and gentlemen. So to continue, Dr. Tien has been selected by the National Academy of Engineering to participate in 3 Frontiers of Engineering Symposia, and has also been selected to organize the Frontier Engineering Symposia and Reliable Infrastructure at the U.S. Frontiers of Engineering Symposium and speak on community resilience, years of science, engineering, and medicine. Without further ado, let me warmly introduce Dr. Tien, and Iris, I turn it over to you. We look forward to your talk. Unmute Dr. Tien, please.
All right. Hopefully you can hear me now. Is that correct?
Okay. Yeah, we can hear you now. Sorry about that.
Hi, it's my pleasure to be here today to talk to you about work that we're doing looking at interdependent infrastructure systems and ways that we can perform risk assessments of them. And so let me go ahead and get started. So the motivation, as Randy alluded to in the intro, is that we know that there's increasing connectivity of critical infrastructure systems and increasing dependencies across both these systems and also the functions that they provide for the nation. And so one of the goals of the work and this research project was to really move from looking at a single system to looking at multiple infrastructure systems together. In doing that, then there are different types of interdependencies that arise between these systems, and we want to be able to capture those in assessing these critical infrastructure networks. So as an example here, I've shown on the right here, water, power, and gas networks. They are all overlaid on each other. They have dependencies between them. And so because of these dependencies, there are different scenarios that we want to be able to capture and analyze. The first is what I've listed here as a threat of cascading failures. So this is the idea that if there's a failure in one system, it can affect not only that single system, but also cascade through that network to other networks as well. So we want to be able to capture that threat of cascading failures. There are geographical hazards that we want to take into account. So since many of these networks are overlaid on each other, they have similar geographical hazard exposures or even other types of hazard exposures that might be common across components that are located together. We want to be able to capture that. And then looking at resilience and really thinking about what does resilience mean and recovery, that there are different infrastructure networks that have to be operational and that certain systems will depend on other systems in order to facilitate that sort of recovery. And so these are the types of interactions and relationships between infrastructure systems that we want to be able to capture in any sort of risk assessment. So in the talk today, I will begin with talking broadly about a methodology that we've developed and built for interdependent infrastructure system analysis, and then really focus on how we're transitioning that from a research space and from a research project and research advancements to a software tool that we are calling PRISM. And so I'll give a short introduction to the methodology. I've shown a schematic here, and I'll go into a little bit more detail over the next few slides on this methodology, and then focus on how we are translating that into the software tool PRISM, a screenshot of which is shown on the right here. And then I'll go through 2 example analyses to illustrate what PRISM is doing and will be capable of doing as we're developing the software tool. So to talk in more detail about the methodology, so this is a flowchart of the many steps and many elements of the methodology. As you can see, it's a multi-step process, and there are multiple steps in this, and each of these steps have accompanying algorithms that go along with that. I won't go into the details of all the algorithms here, but I do want to draw your attention to 3 main aspects of this overall methodology for interdependent infrastructure system analysis. So the first is going to be the individual component characteristics that we are taking as our inputs. And so when we're looking at these infrastructure networks, they're made up of a bunch of different components. There's all these individual components that are operating together to provide a service, to provide some functionality that the infrastructure system provides. And so this top level layer here that I've highlighted here are going to be our inputs, and they're going to be individual component characteristics that the user would input into this analysis. The second main layer that I want to draw your attention to is when we define interdependencies across the system. So this is this interdependency modeling layer here. And I'll talk in more detail about these specific interdependencies in the next slide. But here, this is the key of looking not just at an individual system and its components, but also looking at these interdependencies across systems. And there are 3 specific types of interdependencies that we've defined that I will talk about. And then the last is that through this multi-step process and with all these algorithms to run these analyses, that we're able to conduct these analyses across a range of different threat and outage scenarios. So that's going to be this last layer here, which we call the inference layer, which is the idea that using these inputs with this modeling, capturing these different relationships, we're able to perform inferences or have these outcomes that include here, I've listed as outage simulations, vulnerability assessments, and critical node identification. So we can simulate what would happen if a certain outage or failure occurs in the network. We can assess the vulnerability of the network in a more comprehensive way than previously possible. And then we can also identify what other critical nodes in the network that you might want to focus on as a user to increase the resilience of your infrastructure system. And so as you can see, there's many steps in this. There's many different components of it. What I wanted to do in the next few slides for the methodology in particular is focus on what's different and special about our approach compared to existing approaches. And that's really in these interdependencies that we've defined across the system. And so I'll talk in a bit more detail in terms of those specific types of interdependencies that we're wanting to capture within PRISM, within this overall framework. And so in defining our infrastructure system interdependencies, we defined 3 comprehensive generalized interdependencies. They're shown here. The first is a service provision interdependencies. This is the idea that one component depends on the service outputs of another to function. A geographical interdependency. This is when 2 or more components are in the same geographical area, so they might be more likely than to fail together under a certain scenario. And then the third is this access for repair interdependency, with the idea that different infrastructure components have to be functional for both cyber and physical access to failed components. And the novelty and the new work that we've been doing in this space is to create methods for quantitative probabilistic modeling of each interdependency type. And so these were things that we identified as not being available in the state of the art in terms of being able to really provide quantitative, rigorous analyses of these systems. And then also the probabilistic side in terms of these threat scenarios, these component behaviors are not known for sure. We don't know exactly what's going to happen. And so to be able to capture those uncertainties, we want to make sure that we have both a quantitative and a probabilistic modeling framework that we're able to capture these interdependency types for interdependent infrastructure systems. So the service provision interdependency is, again, when the functioning of one infrastructure depends on the service outputs of another to function. Examples here are fuel supplies for power generation, and in a water distribution system where there's pumps, for example, electrical power is needed to operate those pumps. And so we're taking a graphical modeling approach. A simple schematic here is shown here, where each of those circles, each of those nodes in those networks, this top layer here represents different components of the network. So we're starting from those inputs. That input layer there was about those component characteristics. So we want to capture each of those component characteristics in that top layer there. We have what we're calling a minimum link set formulation. So this is, the important part of this is to show how the components all work together within the network to provide some infrastructure service. And so this infrastructure system then is on this lowest layer. And in this service provision interdependency, it's that yellow arrow in between those 2 graphs at the top there. That's showing that there's a dependency of the water component, C sub 1 sub W. So the W indicates this water system, relies on a power component, which is C sub N sub P there. P indicates power here. So we're showing that this water component depends on power to function. And of course, within each of those networks, the water component is operating within the water system, the power component is operating within the power system. And so we want to capture that connection then between water and power. And so that's the service provision interdependency. Moving to the geographic interdependency, this is the idea that the functioning of one infrastructure is connected to the functioning of another due to either physical similarities between components in a network or geographic proximity. So examples of this is many gas lines and water mains are going to be located in the same trench, and so they're co-located components there, and so they have a common hazard exposure. If there's some disruption that would impact the gas line, for example, that would similarly impact that water main. And so here I've shown, again, with our graphical network approach, we have our gas and water network that we're looking at. We have different components in that C layer there. And what we're adding now for this geographic interdependency to capture that is this common hazard node that can affect components in both systems. So both the water system and the gas system would have this common hazard node that would impact both of them. So that's how we're going to be able to capture those geographic interdependencies. And then finally, looking at the access for repair interdependencies. So this is something that's quite different from what we've seen in the literature in the past and what people have done in the past. And this is the idea that the ability to repair one infrastructure is going to be affected by the access that's been able to be provided, either that's physical access for example, for repair trucks or crews to be able to access a failed component, as well as cyber and remote access. So as more components become controlled remotely with SCADA systems and other sorts of remote access and control, that cyber connection is going to be critical to be able to access and repair any sort of downed or failed components. And so this is really an interdependency type that we defined to address post-disaster recovery for resilience. So resilience isn't looking just at what goes down, but also how things recover. And so this access for repair is going to address that recovery aspect for resilience. So examples here are going to be communication systems that have to be up for these remote and cyber controls, as well as transportations that might have to be up to be able to convey crews and workforces to access any sort of failed or out components to repair them. So within our graphical network approach, we are adding now an access node. So in this case, we're modeling a road, for example, and so that road provides access to a potential failed component. In the power system here, if component 1 is failed, that component would need access from this access component to be able to be repaired. And then we're also adding this dynamic time element. And so one of the things that we found in these analyses is that the state of the system evolves over time. So it's important to be able to track how the system evolves, have a dynamic system that can evolve over time. And we can track then the previous state of the component in the sense that if it's failed, then we need the access node to repair it. If it's not failed, then actually the access node doesn't matter whether it's up or not, because the system will be functioning as normal. So these are the elements that we added to be able to capture this access for repair interdependency. So that's what I wanted to cover with the methodology. I wanted to focus on those interdependency types because that's really the difference in the novelty of this approach compared to what has existed in the past. And so now this is that, again, that overall flowchart of the methodology, but what I wanted to focus now on is to transition now to how we are taking that overall research methodology and converting that into a software tool, which is shown on the right here. And we're calling the software tool PRISM, which stands for Probabilistic, Resilient, Interdependent Infrastructure System Modeling. And so it's probabilistic. As I mentioned, we're accounting for uncertainties that occur within the network, within components, as well as threat and hazard scenarios that might occur. We're looking at resilience, and then we're looking at interdependent infrastructure systems. So what I wanted to do now is to introduce and talk about the capabilities of PRISM. And so PRISM is taking it has certain inputs that it takes. It's a software tool, so the user will input certain things into the tool, and then it will also have certain outputs. So let's focus on the inputs first. So we wanted to keep it as simple as possible, as low of a barrier to entry as possible. And so we're really focusing just on the critical inputs that have to be input into the tool to be able to build out this network. And so the most straightforward way, and as we've seen in working with different utilities, is having these component characteristics be in an Excel file. And so here in this case, I've shown an example Excel file of a network, and the different aspects and component characteristics that we're using are going to be the characteristics that define those components within this connected infrastructure system. And so these are going to be junctions, which are points in the network. We're looking in this example here at a water distribution system, so they'll be looking at pipes. So pipes are going to be those that connect those points in the network. So we're conveying a water resource from one point to another. Those are connected through pipes. So we'll have junctions as the points, pipes that connect them. And so then that third bullet there is connectivity. So how the network is connected is important in terms of how resources are conveyed across the network. And then also locations, so coordinate locations of all those components. And so we really wanted to make this as simple, as approachable as possible. And so these are really just the 4 bare bones things that we would need to know to be able to run the system analysis. And so within the software tool, so this is going to be the input screen here. And so here we have the data inputs as well as a button there to open and load the file. And so essentially we would just open this Excel file and be able to load this file into the tool as a data input. And after doing that, then it populates those junction and pipe information as shown on the left-hand side here. And then we can click this graph button. And so this is part of what we wanted to do with PRISM, is to make it as visual as possible as well. We could have lists of numbers and lists of probabilities of failure, things like that, but we wanted to make it as visual as possible. So we have a graph button here. And if we click that, then it takes the information that's been input and builds out the graph as we see on the right here. So on the right here, we see the black circles here are going to be our junctions. Our pipes are going to be those lines that connect them. We've differentiated between supply nodes and other nodes here with the idea that supplies are going to be where the resource is coming from, and they're distributing to those nodes through the network. So here, this is the graph then of those inputs that we had for our junctions and pipes. And so those are going to be our main inputs for the tool. And then now I wanted to talk about the two example analysis scenarios that I'll go through today. The first is going to be a pipes analysis. So we're going to focus on having the pipes as our components in our network. And the idea here is that there's different tools that are available to simulate, for example, pipe breaks in a hazard. And so if we have then this upstream simulation of how likely it is for a pipe to break under different sorts of scenarios, then we can take that information and then put it into the PRISM tool, which would then include the service provision interdependencies that I talked about earlier, to then be able to do a vulnerability assessment of what the impact of different failures of the network is and as they cascade through the network. So this will be our first analysis scenario that we'll look at. The second scenario that we'll look at is focusing more on junctions as our components that we are interested in the network. And so here we're looking at the points in the network. And here this is going to be more broad and more comprehensive. So the first analysis, we are just going to include those service provision interdependencies. And then the second analysis here, we're going to have those service provision interdependencies, but then also add in the hazard nodes and the access nodes to the network for those geographic interdependencies, as well as the access for repair interdependencies that I talked about. So this second analysis scenario is going to be more comprehensive and broader to be able to do this interdependent system risk assessment. And so I'll go through now each of those analysis scenarios, step through what the inputs are, and what types of analyses can be run for each of these scenarios. All right, so looking first at the pipes analysis. And so now this is going to be the second tab in our tool. So here we're now at our analysis options tab instead of the data inputs tab. And so what we're going to do is we're going to select and configure our interdependencies. And so we have here selected pipe components. And since we have that upstream simulation, we're not going to have hazard or access nodes here, but we are still going to configure the service provision interdependencies. So if we then click, there's this configure supply interdependencies button here. It'll pop up this window here, which is where we configure those inputs. And so here we're going to open and load a file for probabilities of failures for the pipes. And so again, we're the whole process, as we saw from that initial flowchart of the whole methodology, is quite complex. There's many steps, there's many different algorithms that are underlying it. What we're trying to do with this tool is to make it as straightforward as possible, as intuitive as possible in building out the different aspects of the whole system. And so here for the pipes, we're going to open and load a file. So here again, we're using an Excel file as a standard, kind of most simple approach to upload data. And so here we're looking at pipe probabilities of failure. And so in this case, they're going to be simulated likelihoods of pipe breaks in a hazard. And so this is the idea that with an upstream program that you can simulate in a given scenario, for example, for an earthquake scenario, or it could be a more targeted attack, you would have these different likelihoods that different pipes would break. So we have then these probabilities of failure that we're calling P sub ep here for these pipes. So we're going to open and load this file into the system. And then we're going to have here now on the right here, you see the header, there's power and access components. So these are going to be more of those interdependencies. And in this case, we're going to focus on the power components. And so we're going to have service provision interdependencies, which are going to be power supplies at the water supplies. And so in this example here, we are looking at a water distribution system. There's different water supplies providing water to different distribution points. And so for each of those water supplies, we're going to say that they require electrical power. We want to capture that dependency between water and power. And so we're going to have a service provision interdependency captured here with a number of power supplies at each of those water supplies. And then each of those power supplies in turn can also have a probability of failure. So we could also look at how the probabilities of failure or outage scenarios change if you have, for example, power backups at those water supplies, if you have additional, if you have multiple connections back to multiple substations, if you have generators at your power supplies, how would that affect the outcome? So that's what we're trying to capture here with our service provision interdependency and specifically our power supplies for our water supplies. All right, so this is going to be then, once we input all that information, this is going to be how the analysis options tab is populated. So on the left, we see that we have the power components information populated there, and then the graph on the right is a new graph here, which is plotting from probability of 0 likelihood of failure up to the red would be 100% likelihood of failure, given those input values of the pipe probabilities of failure. So here we have the squares are still going to be our water supplies. Our circles are going to be our junctions. You see those different levels from green in this case to a little bit of a lighter yellow-green there. And those are showing the likelihoods of different pipe breaks, different pipe failures given those simulated scenarios. So again, that color gradient is going to be what we're going to look at in terms of changes between likelihoods of outages and failures across the network. All right, so now that we've input all that information, then we can run analyses. And so now this is going to be the third tab that we have on our PRISM tool here, which is to run analyses. And the first thing that we're going to do within this tab here is to update our graphs. And so if we click update graphs, what happens is that it loads that right side graph here is now going to be on this left side here as edit selections. And then that middle graph is going to be our hazard selections. In this case, we're not going to have an updated hazard graph, but in the second scenario our second example scenario that I'll show you in a second, after this pipes analysis, you'll see those different hazards groups selected. And so in this case, we are updating our graphs. This shows those initial input information. And then we have now this tab, which is going to be this run analysis tab, which is going to be where we're running our inferences. So if we recall our initial full methodology with that, all those boxes, all those connections, the multi-step process, that bottom layer there was our inference layer. And so that's the idea that we have all this information, we're capturing all our interdependencies, and now we want to actually perform an inference or run an actual analysis on our system. If we click this button now, what happens is that it takes the information that we've input, so all the component level information, all of that service provision information that we have, and then it will take that input information and then build out our full network. So here I'm showing, this isn't shown on the actual tool, but to give you a sense of the back end there, which is not shown on the tool, but what's running in the back end of the software tool is that taking that input information of component information, those component locations, component connectivity, that graph there, it builds out this full graphical model. So this is going to be what's shown here with the yellow circles here is an example of the graphical model that's built. So obviously it's very complex. There's a lot of different nodes in this network model. This is what we're using to capture all those interdependencies. And so that's the back end, that's the engine that's running behind this software tool. And it's taking that then, and then it'll show the results here on this right-hand plot here, this analysis results plot here, which is showing from those inputs, building that full network model, running the analysis, having that whole engine run, these are the results here. And so for the user, they just see this right-hand plot here, and we could see now the analysis results from this initial analysis. So from our initial analysis, we can see the difference between this left-hand side and the right-hand side here. There are pretty subtle differences here because we have a relatively robust network in this case, but based off of these results, then we can run and analyze potential failure scenarios. So I'll go through a couple examples of potential failure scenarios and how a user might interact with this tool to analyze vulnerability of this system. So in the first step here to analyze potential failure scenarios, let's say we wanted to look at this network and we want to say, well, if one of the supplies fails, what's the impact on the rest of the network? How big of an impact would that have? And so we're going to take our left-hand screen here, this edit selection screen. I've drawn a box around this supply node that we're going to look at. And we're saying, well, if this supply is out, how much does that affect the rest of the network? So what we've created is that we can actually click on that node in the network and select it. And so this is what is done here. So you can click on the node in that network on that left-hand graph. We wanted to make these graphs interactive as much as possible so that a user can interact with these graphs and not necessarily know that this is supply node number 2, but you can click on that node. It would pull in from the back end that node information. So we see that it's indicated as node number 2. We have the X and Y coordinates there. And then we want to say, well, let's say that this supply has failed. So then we can click on that failed button there. So we selected the node from the graph. We input a failure scenario here that this node has failed. Then we can go ahead and click update here. And then what that will do is that I'll update that right-hand graph there. So if we look at our analysis results graph, we see that with that supply failed, we see the then failure of those two pipes that are connected. So looking again at our color bar, but we still have green going from good, totally no problem, survived components, to red is going to be failed components at 100% likelihood of failure. We see that change then from the green from the past initial analysis to, if we have this failure now, those pipes become red, and this is showing the extent of the outage if there's a failure in that supply. And we can do multiple runs of these things, and so we can say that, well, now let's say we also have a situation where this supply might be out, and so we can do something similar. We can click on that node, select it, we have a node failure scenario, we can update our node failure scenario, and then we have the outcome on the right here. And so here we see, so we had those bottom two supplies be out, and we can see the extent of the damage there. In this case, we see that it's actually relatively well contained. The pipe impacts are not spreading through the whole network. And this is a case for this particular network because we actually have many supplies to the network. And so that's an indicator of enough redundancy in the network to be able to accommodate those failures. And so in this case, even if we have two failed supplies, the other nodes are able to receive the resource that they need from the other connected supplies. And so this is the case for this network. If you had a different network which had fewer supplies, for example, less redundancy in the network, then we might expect then a single failure in a single supply might propagate through more of the network. But this is a case here now where we are able to actually quantify what are the changes in likelihoods of failure for different components of the network given different failure scenarios. And one of the other things that we can do then is, let's say that bottom rightmost node there, maybe that's supplying water to a critical facility, maybe a hospital or an emergency shelter type facility. We can look at what are the likelihoods that we can maintain that functionality to that critical facility under different scenarios. And so even under this, in this case, under this failure scenario, we would have an outage at that rightmost point. Potentially, if we added different links, if we were able to have a backup, we might be able to protect that critical facility from having an outage under this specific outage scenario. And so this is an example of that vulnerability assessment that we're able to conduct using this tool. And so here, I'm indicating that this is a vulnerability assessment to potential cascading failures. So in this case, we could also model potentially a failure in the power system that would indicate a failure of that water supply node that would then cascade through outages to the water component nodes outside of those supplies. So we can capture that chain of events that could happen, those failure scenarios that would happen, and go from one component to another to look at those impacts at a system level. All right, so that was what I wanted to cover with the pipes analysis. I'll go ahead and move now to the second analysis that I mentioned, which is now our junctions analysis with added interdependencies. So compared to that first pipes analysis, we just had that service provision interdependency that we cared about. In this analysis, now we're going to add now access and hazard nodes. So we're going to go back now to our tool in our analysis options tab. And so now to indicate that we want to add these interdependencies in our analysis, we can go ahead and select and configure our interdependencies. So in this case, we've selected junction components. And we've also selected hazard and access nodes. We want hazard nodes and we want access nodes to be able to capture those two other interdependency types. And so now when we click on configure supply interdependencies, a different window will pop up because we have these more interdependencies that we want to capture. And so what's different now about this screen compared to the previous screen is that we have this whole middle panel here. And this middle panel is looking at both power and access components. And so this is looking at the service provision interdependency as well as the access for repair interdependencies. And then we have the right panel now, which is also new, which is now going to look at our hazard selection. And this is really focusing on our geographic interdependencies. And so in this scenario, this is our more comprehensive interdependent infrastructure system analysis. We're including all three of those interdependency types that I talked about: the service provision, the access for repair, as well as the geographic interdependencies are all captured within the tool now. So now I'm going to go into some more detail in terms of how do we actually input this information and how do we select it. So let's look first at this hazard selection box here. So on the right-hand side here for these geographic interdependencies. So what we wanted to do is, so these are going to be our interdependency inputs now. What we wanted to do with our hazard selection is that we know that our hazard selection is going to be based off of geographic areas. Rather than having a user actually click on every single node and say which group it's in, we actually created this interface, this interactive graph here, as we show, as you can see on the video on the left here, is that the user can actually select and bound which different hazard groups it should be in. And so in this case, the user is selecting this group of nodes on the left. Once those have been bounded, you can press enter and then click on the graph to confirm that those nodes all belong to one hazard group. You see them show up on the legend on the upper left as hazard group 1. And then you can then select a different group of nodes. In this case, we're going to select these right-hand group of nodes as a second hazard group. And we've clicked enter to confirm and selected, and you see it show up on the legend as hazard group 2. And then for each of these hazard groups then, on the bottom here, you see hazard group 1, hazard group 2. You can have different probabilities of hazard occurrence for these different groups. So this is what we developed in terms of enabling a user to select these geographical areas for different hazard groups. And so you can group these nodes together by geographical location. Say that all of those nodes, in this case the blue nodes, are going to be subject to one hazard. The green nodes are going to be subject to a different hazard, and these two hazards could have different likelihoods of occurrence. So we're calling this hazard here. You can think of them as geographical hazards like a storm coming through or an earthquake or some subject to a tornado or a flood or something like that. You could also potentially see them as a more targeted attack. If there are certain components that are more exposed compared to others, we could have those be in a hazard group compared to a more protected hazard group. Perhaps is it going to be a group of nodes that are more protected. So the idea here is to differentiate between different hazard groups and really look at those geographic interdependencies between the nodes. So this is the idea where you have those different hazard groups affecting different groups of nodes within a network. So that's going to be our hazard selection interface there. And so once we've selected those hazard groups, then those are going to show up on our right-hand panel here within our hazards box. So that graph that I just showed is now going to show up here on the right-hand side here. We have our blue nodes and our green nodes showing those different hazard groups, as well as the different probabilities of hazard occurrence. Now we're going to focus on our left-hand panel here. So similar to before, we need to input probabilities of failure for our junctions and our pipes. And so here we're going to, again, take as simple Excel files. So we want, again, this to be as straightforward as possible. And so just simple Excel files with different probabilities of failure. So in this case, these are going to be likelihoods of component failure under a no hazard or hazard scenario. So the idea here is that for each of the components, given how robust it is, how much strengthening or retrofitting it's had, it could have a different likelihood of failure given a hazard. So if that threat happens, if that hazard happens, if that event happens, how likely is it to have failed versus under just normal operating conditions, the hazard did not happen, that threat or event did not happen, what's the likelihood of failure? So we want to input those. In this case, we're going to just open and load these files, and that'll go ahead and populate all of those values for the components. And then finally, we'll look at this middle panel here. So this is going to be looking at our power components. And so this is going to address our service provision interdependency. We have the probability of failure for our power component, as well as the number of power supplies at each water supply. That's looking at our service provision interdependency. And then on the right-hand side of this panel here, we have our access components. And so this is going to be looking at the access to repair. So we have now, we also need to look at how likely that access node is going to be operational given a hazard, and then also the number of access components. So you can imagine if you have, let's say, a component that needs remote access to be able to ascertain the fault status, to be able to push any sort of patch or change. If you have just one communication channel that can work on, that would be one access node. If you had a backup and you also had a second communication channel that you would be able to access that node, you would have two access components for that component, and so you'd be able to input that there. And then on the very bottom right there, we have a probability of repair. And so this is the idea that even if you have access, there might be some likelihood that the component would be able to be fixed or not. So in this case, we're putting 80% there as a probability of repair. We're saying if a crew is able to access this component, there's an 80% chance it can be fixed. If we're able to gain cyber access to the component, there's an 80% chance that we can send a successful patch to fix that component. And so these two parts of this panel here, the power and also access components, are where we're really addressing the service provision interdependency, as well as the access for repair interdependency. And then that right-hand panel is going to be our geographic interdependency. So those are going to be all of our inputs. And so with these interdependency inputs, we've input all that information. We have our initial analysis options tab here, and that'll, once we've input all our interdependencies, those three that I talked about, it'll populate this whole screen here. So this is automatically populated now, given that information that was input in the previous screen. And so this is for a junction analysis with both hazard nodes and access nodes, as well as looking at those power nodes for power supplies. All right, so that's going to be all of our analysis options that are going to be input for this analysis. And then we can move on to our run analyses and our run tab. So now we're going to go on that run tab now. We're on that third run analyses tab. And I'm going to go ahead and update our graphs and run that initial inference analysis. And that'll populate the tabs, the graphs as shown here. And so here on the left-hand side, we have our edit selections graph. So that's going to be the graph that we're going to manipulate if we wanted to make any changes to see what the impacts would be. In this middle graph here, we have our hazard selections graph here. So this is going to be those two hazard groups that we previously selected. We can see that they're shown here. And then on the right-hand side here is going to be our analysis results. And so in general, for a user, the workflow is going to be that they can take this edit selections plot on the left, make any changes that they want, and then by hitting run analysis on the top there, it would show up on the rightmost tab, rightmost graph there as our analysis results. We are showing these analysis results graphically here to be able to visually assess any sort of changes and impacts. We also do have an export file option there, so we can actually get actual numbers of what those analysis results are. And so now I'll go through a couple example analyses in terms of what we can show for failure analyses and the impacts on the analysis results. And so here we're going to look at a supply node again, as similar to our pipes analysis, but we want to see if this supply node fails, what would be the impact. So if we can go ahead and select that on the graph, we update this as a failure scenario. So we select that failed status for that node, click update, and on our right-hand side there, it's running through that whole algorithm. We're running through that whole back end, that complex graph there. Running through that, all of that is hidden from the viewer, but then the result is shown on the right here. And we see we have a failed supply node, and then we have a failed now right-hand side junction there, as showing as red, as showing as likely to have failed in that scenario. And then let's say we now do something a little bit different, is to look at a non-supply node. So previously we were looking at, well, if a supply node fails, what is the impact on those distribution nodes? What is the impact on being able to provide a resource or a service across the network? But we can also look at non-supply nodes. So here I'm selecting a node in the middle of the graph here. And so here, if we select it, it's node number 20 as indicated there. As I said, the graph, it's an interactive graph, so we can click on the node, it'll pull up that information, show it as node 20. We can select it as failed, and what that's doing now is it's updating on the back end the state of that node within the whole network. And then running that analysis again, we get now what's shown on the right here, which is boxed in that red there. And so what this is showing is that, so we have that failure scenario where that node in the middle, that circle has failed. And we can actually see now some updates on those supplies that are supplying that node. And so we see that it actually goes from a darker green to this lighter green. It's a bit of a subtle difference, but we can see that difference. And if you exported the numbers, you would see the actual quantitative difference there. But what this is showing is that we can actually do a backward inference and look at the causes of a failure for this more comprehensive risk assessment. So in this case, we can say that, let's say we've observed a failure at that supply node, that middle circle there. Let's say we have a facility there. We've noticed that the water pressure is down. We don't have water service there, for example. We can say that if we've observed that failure, so that would be that edit selections input, we input that that node had failed. We can say, well, what is the likely cause of that failure? And so here we can say that there's that updated likelihood of failure of those two supplies that are closest to it. And so we're saying that that's showing a backward inference in terms of, now that we've noticed this outage at this distribution node, how likely is it to have been caused up by this supply nodes? And those two supply nodes are going to be the most likely sources of that outage. And it's important to note here that in all of these analyses, we've included all of those interdependencies. It's hidden from the viewer in the sense that the viewer doesn't necessarily need to know all the details of how it's being modeled and all of those dependency relationships that we're capturing, all those graphical arrows that we have between the different nodes in the graph. But the outcomes here, the analysis results on the right-hand side, are those analysis results that include all of those interdependencies. So including the service provision interdependency, that is the power supplies for those water supplies, including the geographic interdependency, so looking at those hazard groups, looking at those blue nodes in the middle there are more likely to fail together versus the green nodes. And then also including those access for repair interdependencies, looking at how many nodes we have for access and those probabilities of repair. And so really this is two kind of straightforward examples of those analysis scenarios that we can run, but we're continuing to build out the capabilities of the tool to run different types of analyses and more complex combinations of different analyses that can be run. And so as a reminder then, this whole backend part is the part that is really the crux of the tool. So this is all of the backend algorithms and building of the network diagram that we see here. And it's all running when you just click an update button, and that run analysis button, it's building out this whole network. It's running the analyses, updating the states of these different nodes. But with the tool itself, all of that is really hidden from the viewer, and what the viewer and the user would care about is this right-hand graph here and the analysis results and outcomes for the tool. And so with that, I wanted to kind of summarize what PRISM is all about. What we want to really do is to take relatively simple inputs, so just component characteristics. All we're looking at is component locations, what functionality they have, essentially if there's a supply or not, and those vulnerabilities, so how likely they are to fail under different hazards, and then the connectivity between the components. Just those 4 component characteristics are all it's taking as inputs. And then based off of those inputs, the outputs that PRISM is able to provide are the system vulnerability assessments, looking at the vulnerability of the system as a whole based off of those individual component inputs. We are able to assess potential cascading failure impacts. So if we have an outage at a supply, how far does that propagate through the network? Is it well contained? Is it only going to impact a few nearby components? Is it going to impact more components through the network? And then for all of these outputs, we're including service provision, the geographic in terms of those hazard areas, and also access for repair interdependencies in all of the analyses. And so really, we're trying to take relatively simple inputs, relatively low barrier to entry in terms of what needs to be input into the tool, and having quite sophisticated outputs in terms of those system level vulnerability assessments, cascading failures, and including all 3 of those interdependencies. And one of the novelties of what we're doing compared to what has been done in the past is that we can take very specific component level information. So where a component is, if it's been retrofitted or not, does it have a lower probability of failure in a hazard, and really translating that component level information into these system level outcomes. And so with these system level outcomes, we're able to then have this more comprehensive view of risk for critical infrastructure and perform these more comprehensive critical infrastructure risk assessments. And finally, the differentiation of this approach compared to what has been done in the past is that the first aspect is that quantitative aspect. And so rather than saying we have an increased risk because we only have one power supply and we don't have a backup, we can actually quantify the difference in risk outcomes if we have these different changes in our system. And so we're able to quantify those impacts and quantify the risk for the system. And then the second main part is that it's probabilistic. And so as you might have seen in all those inputs, we have probabilities of failure, we have likelihoods of pipe breaks, we have likelihoods of hazard occurrence. And so in a world that's very uncertain in terms of what our component outcomes would be, what our potential threat scenarios are, we're able to account for those uncertainties and really capture all those uncertainties within the PRISM tool. And then we account for these interdependencies both across systems and functions within the tool. And so with that, I wanted to acknowledge a lot of the main student work that went behind the development of this tool. Chloe Applegate did a lot of the work in the beginning in terms of defining those interdependencies, building out that flowchart in terms of those different components and algorithms that have to be operational to make this analysis work. Cynthia Lee did a lot of work in terms of refining that algorithm, converting that algorithm from a research environment into a more operational environment and a translational environment for users. And then both Cynthia Lee and Shirley Xu have been working on this user interface, building out this user interface for those inputs, as well as visualizing those outputs for analysis. So with that, I want to acknowledge Siri and the support for this project through the Department of Homeland Security and this award number. Provide my contact information here below, and I'm happy to take any questions or any comments about our tool. And as I said, we're continuing to develop this, and so we'd be happy to kind of incorporate any sort of capabilities or functionalities as we're continuing to build this out and finish this out. So thanks very much, and I'm happy to take any questions. Thanks.
Unmuted.
Iris, there is a question. Oh,
Randy, there's a question in the chat from Ed Midden. This is an impressive tool. Is it being used anywhere? And what level it's supporting infrastructure decisions in municipalities?
Yeah, so yeah, it's a great question. So I'll talk a little bit about the genesis of this project and why we even thought such a tool was needed. And it was through work that we did with the City of Atlanta, and specifically working with their Department of Watershed Management. And so they're the people who manage and operate the water distribution in the City of Atlanta. And what we found was that actually most of the outages that had occurred in the recent past was not due to actual outages within the water system itself, but actually due to the dependencies on power. And so it was really cases where there was a power outage that then led to a water system outage. And so being able to capture those dependencies was something that was missing in practice with municipalities and with the department. And so that was one of the main impetuses for this research project to begin with. And then now I'll say that we're continuing to interact with them in terms of implementing and kind of utilizing or seeing what type of information they would need for this tool. And so one of the things that we're hoping once it's built out is that we'd be able to identify which supplies, for example, are the most critical in providing generators and power backups, for example. So that's one of the concrete decisions that they are continuing to make in terms of increasing resilience for the water system, is identifying the locations that are critical for having power backups. And so I will say, in the process of doing this, since this has taken some time to develop, there was one that was selected, but we're hoping that as we continue and are able to develop these capabilities, that we can implement that into processes in terms of identifying where those critical points would be. I'm actually going to pull up the chat here to see if there is.
Timothy is asking if the talk will be available by video. And yes, we are recording it. We will be posting it on the CIRI website, but we will send an email to all of the CIRI mailing lists, letting them know when it's posted. Timothy, if you want to put your email in there, I can let you know when it's posted as well.
And actually, I can speak a little bit more in terms of other infrastructure decisions and other municipalities that we're starting to work with as well. So we're also starting to work with the city of Savannah at the Georgia coast. And so there's a different set of hazards and threats that they are concerned with. But we're hoping that and one of the things that we've been talking with them about is looking actually not just at water systems, but actually looking at critical facilities and all of the infrastructure that supports critical facilities in emergency situations. And so by looking at those dependencies across those different systems, that it would support emergency response. So we're working with, for example, the Office of Emergency Preparedness there, the Emergency Management Agency there, and also the city of Savannah to look at what types of dependencies do we care about the most, which are the most important in terms of emergency preparedness and response as well. I see a second question here. I can go ahead and answer that if that works.
Go ahead.
Yeah. So I see a question about a real-time setting with inputs are sensors with information about availabilities and outages and addressing some of the challenges for that type of deployment. Yeah, so that's definitely something that we have been thinking about. And I think one of the advantages of this approach is this updatability. And so I didn't talk too much about that backend, but really that graphical network approach, it's based off of a Bayesian network approach, where one of the advantages of such an approach is its ability and ease for updating with new information. And so the examples that I gave were to show like you clicked on a node and that failed, but definitely the idea of a potential automated system where rather than a user selecting those for potential scenario analyses, that you would have it running in the background where if it took as an input a potential failure that it saw, that would actually be then that update. It would be an automatic update where that node would fail and then you could see in real time the impacts across the network. And so there's those two aspects now, right? I will say right now we're focusing on more of this user scenario analysis, like running what if scenarios, running potential vulnerability assessments, but definitely having that capability of doing an automatic updating would be relatively easy to implement in terms of just tying it into that monitoring system, essentially. So monitoring, having that sensor information come in real time and then update those nodes and then having that automatic run analysis push for that outcome would definitely be a possibility and something that we would like to see happen as well.
So there's a couple more questions. I want to try to make sure we get through them. One was a little bit earlier from Ed. How long did it take to develop the model for Atlanta watershed?
Mm-hmm.
Wondering how difficult it would be to model a city like New Orleans or Houston.
Yeah, so I'll say the longest part was actually getting the data from the city of Atlanta. So just data sharing agreements. As we know, a lot of this data is sensitive and we don't want the data to be distributed beyond the needed parties. And so that data sharing was actually a long process in terms of going back and forth and making sure that it was being shared in the correct way. But once that sharing actually happened, building the model is relatively straightforward. As I said, we just have those 4 component characteristics that we need. And so if the data is available, it would be relatively straightforward to implement for a different system in a different city.
Okay, and David asks, I've seen that most of the component probabilistic failures are theoretical. Do you have any actual practical or real data about those?
Yeah, that's a good point. So in this case, we did input uniform probabilities of failure except for the pipe break one. So actually, let me say for the pipe break one, those are simulated based off of practical, like empirical analyses in different events, what have been the number of pipe breaks per kilometer or per meter. And so we actually use those empirical relations to do those simulations for the pipe breaks. And so that I would say is based off of real data for those values there. In terms of the other probabilities of failure, it is a little bit trickier because there isn't as much data available. In our case, we decided to go with the uniform number to say that if we started with everything being the same, what would be the impacts? And so that was the approach that we took in terms of analyzing across the system. There are, in talking with other utilities and departments, there are some things with like asset assessment or asset scores that we've thought about using as a proxy for a probability of failure. So based off of age or retrofit or material, these the entities assign a health score essentially for an asset, and so using those as a probabilistic failure likelihood is also a possibility.
And one more quickly from Jim. As word of PRISM gets out, how much training will need to be provided and adjustments made for different localities, and who can support that level of training?
Yeah, so we are, as we're developing this, we're also building out like a handbook, a guideline of how to use it. I will say we haven't talked too much about like ongoing support and training. Right now it's really like me and my students who are building it and would want to support any sort of like troubleshooting or issues with that. I think that's probably something that Siri and I can talk about potentially in terms of like sustaining such a tool and having ongoing technical support for users of the tool.
Yes, indeed. I mean, that's part of our mission here at Siri, is to engage in technology transition. The important part is to get this tool out into the field so that it's going to be used and the impact can be felt. So we will be working with Iris on that. So we're out of time. I want to thank everybody for joining. Thank you very much, Iris. It was a great presentation. Really appreciate it. Very packed in presentation with lots of great information. Appreciate it. And thanks everyone for attending. We appreciate it. See you next. Be looking in your emails for announcements of the next webinar. We're still working on the schedule for that. Thank you again for attending.
Thanks.
Bye-bye.